Hey students, so in this video I'm going to show you how to do inferential analysis. And as you know from class, there's two types of inferential analysis. You could either do a parameter estimation, which means you have no preconceived notion of what the parameter, the population's value could be. You're basically just asking SPSS to generate a confidence interval that will tell you between which lower and upper limits that actual population's parameter will fall. Or secondly, instead of parameter estimation, you could also do hypothesis testing of a population's parameter. And in this case, you do have a preconceived notion. You do have a certain idea or hypothesis about what you think the population's parameter would be. And what you do in SPSS is test whether that is correct or not, based on your samples statistic. So I'm going to show you both methods consecutively. So in order to do so in SPSS, we need to work with a metric scaled variable. So either an interval or a ratio scaled variable. And it just so happens that in the previous video we created this index variable for subjective knowledge, and this is a perfect example to use for inferential analysis. So if we now want to, for example, in the first case, know what the population's subjective knowledge is, of course we could calculate what the sample's subjective knowledge is, the average subjective knowledge in our sample, which we can do by means of simple descriptive analysis. But what if we want to know between which boundaries the true populations, so the population's parameter subjective knowledge falls? In that case we have to do inferential analysis. So we click on Analyze, we go to Compare Means, and then we go to One Sample T-Test. And under One Sample T-Test is where you find the inferential analysis. So we click One Sample T-Tests, and what you have right here, and actually let me reset that for a second because I had something in there from a previous analysis. You'd go all the way down and find your subjective knowledge index variable. And you click it in. Compute subjective knowledge index variable. Okay, this is the one we want to use. Now, like I said, there's two types of inferential analysis. In the first type, you only do a parameter estimation. With a parameter estimation, you are going to ask SPSS to generate a confidence interval. And in order to do so, you have to leave test value at 0. So by default, it's set to 0, and you want to keep it that way because you don't have a test value. The test value is what you will fill in the second type of inferential analysis later, where you do have a hypothesis. So for now, we leave test value at 0 because we do parameter estimation. All we have to do, and that's literally all, is click in the variable we want to analyze, keeping in mind it should be a metric scaled variable, and then click OK. This is what our output shows. So in our output we get two tables. The first table shows you your sample statistics. So it'll show you for this particular variable, namely the subjective knowledge index variable that we created in a previous video. We see how many people answered it. We see what the average answer is, or the average subjective knowledge is in our sample. So in our sample here, we know the standard deviation and so on. Cool. Now, what we really wanted to do with this analysis, with this inferential analysis, is find out between which boundaries, so which lower and upper limits, the confidence interval is for the population's parameter. So in other words, what would the population's subjective knowledge be like? Between which boundaries would the true population's subjective knowledge fall? So we therefore look here, right here. 95% confidence interval of the difference. So we look at the lower and the upper limits. So we know now that the true population's parameter, so the population's subjective knowledge, will fall somewhere between 3.20 and 3.50. So somewhere between 3.2 and 3.5 will be the true population's parameter. And this is something we estimated, so we did a parameter estimation based on our sample mean. That's all there is to it. Okay, so this is the first type of inferential analysis. As you can see, test value is set to 0. All we do is look at the lower and upper limits for our confidence interval. An estimation basically implies you need a lower and upper limit. Now, let's minimize this for a second. For the second type of inferential analysis, we do have a preconceived notion about what the population's parameter could be. So we click Analyze, Compare Means, One Sample t-test, and so that's the same as before. We click One Sample t-test, we use the same test variable, we still use the subjective knowledge index variable that we created in a previous video, but this time, since we are now no longer doing parameter estimation, we're actually doing the testing of a hypothesis about the population's parameter, we can fill in our hypothesized population's average here. So, for example, think of this question itself. It is about subjective knowledge about craft beer. What if I think that the population knows a lot about craft beer? I'm actually very optimistic, and I think on a 5-point scale, and remember this was a 5-point scale, from strongly disagree to strongly agree. If I think that on a 5-point scale, the average population's subjective knowledge would be 5, I would of course be like ridiculously optimistic here and thinking that everyone has very high subjective knowledge. But yeah, let's suppose I think it's 5. Or what if I hypothesize that the population's parameter would be 4? So that means I still think people have high subjective knowledge, but not like as high as 5. Or what if I think that the population's subjective knowledge would be only 2? So people, if I think that people think they don't know much about craft beer. So this is arbitrary. You fill in what you think the population's parameter would be. Now let's go to our first example, and let's say we think that the population's parameter would be 5. Let's see if this hypothesis of 5 is true or not. Hit OK. And this is what our output shows. Again, for just as with parameter estimation, also with hypothesis testing, we have 2 tables. The first table, again, will give you your sample statistics. So we'll tell you how many people answered, what the average answer was, so the average subjective knowledge in your sample, standard deviation, and so on. Now this here, the second table, will give you the results for your hypothesis testing. As you can see now, test value is 5 because we entered 5. I just entered 5 because I thought that the average subjective knowledge of the population would be 5. Now, there's 2 places where you can look. You can either look at the t-score here, or you can look at the significance two-tailed. This is your p-value. We often call it a p-value. So let's start with the first one, the t-score. This t, as you know, based on the classes, is actually a z-score. But SPSS always reports it as a t. So it's slightly confusing. Don't worry about it. It is basically a z-score in disguise, but it's reported as a t. So this t-score has a certain number. In this case, let's take a look, minus 21.758. Now what you use as a benchmark to evaluate this number is the z-score of 1.96. The reason why we take 1.96 is because that is the z-score corresponding to 95% confidence. And in research, we adopt 95% confidence as a default standard, basically, as the norm. So under 95% confidence, which corresponds to a z of 1.96, and we are confronted with this z-score, or this t-score actually, of 21.758. This number, and you can actually just look at the absolute values, you can even ignore the minus sign, just the absolute value 21.758 is larger than 1.96. And since it is larger, it means that it falls outside the acceptable region. In other words, we have to reject the null hypothesis, which means there is a difference between our hypothesized population's value 5 and the sample value, or the sample's mean, 3.35. In other words, our hypothesized population's value of 5 is wrong. So this is something you could have deducted from this t-score. If your t-score in absolute values is larger than 1.96, then your hypothesized population's value is incorrect. A second way to come to that conclusion is looking at your significance two-tailed. Now this significance value, two-tailed, shows how much support there is for the null hypothesis. And as you remember from the theory classes, a null hypothesis always says there is nothing. There is no difference, no effect, no correlation, nothing at all. But so this significance value, two-tailed, shows you how much support there is for the null hypothesis. Well, guess what? In this case, the number is 0.000. So there is literally zero support for the null hypothesis. Conversely, if there is no support at all for the null hypothesis, we have to basically go with the alternative hypothesis. And the alternative hypothesis says there is a difference, or there is an effect, or there is a correlation. In other words, there is a difference between your test value of 5 and your sample value of 3.35. In other words, if there is a difference between these two, that means one of them must be incorrect, which means we come to the conclusion that our test value is incorrect. Okay, so this is all you look at when you do hypothesis testing of a population's parameter. You look at the t-score and you look at the significance value. Now, what if, for example, I would have entered another number, not test value 5, but maybe test value 3.5? Maybe we would have come to different conclusions. So let's take a look what that would look like and how to interpret the output. Click Analyze, Compare Means, one sample t-test, and then we keep the same variable, but instead of being crazy optimistic, we now make this into a test value of 3.5. So let's say I think that the population's average would be 3.5, the population's average subjective knowledge. I hit OK. And oh, what did we find now? Well, these numbers stay the same because these are just pertaining to our sample. Obviously, the sample itself didn't change. But we see our t-value here and our significance value right here. Remember, the cutoff point for the t-value was 1.96. What we find is 1.93. So that is lower than 1.96, which means we can accept our null hypothesis, saying there is no difference, which means we can accept our hypothesized population's value. We could have come to the same conclusion by looking at the significance value of the two-tailed significance, or the p-value, which in this case is 0.055, which is larger than 0.05, 0.05 being the cutoff point, which means there is sufficient support for the null hypothesis, and also confirms what we found based on this number, that our test value of 3.5 is correct. Okay, so this is where you look the t-score and the p-value or significance value when you do hypothesis testing. Okay, just to summarize, for inferential analysis, you always click Analyze, Compare Means, one sample t-test. You will click in the correct test variable, which will always be a metric scaled variable. And you either leave the test value at 0 if you just do parameter estimation, or you fill in a test value of choice. That could be anything, whatever you want to hypothesize about the population's value specifically related to that variable. Okay, so that was it.